All right, welcome back. We are here with Professor Stephen Williams of Southern Technical College, and we are continuing on with Chapter 5. This time we are talking about three-phase alternating current motors.
Okay, we're into part 3. Previous 2 parts dealt with basic generator action motors, how they work, and we talked a little bit about DC motors. Now we're going to be talking about three-phase alternating current. Seems a little strange to jump right into three-phase, but three-phase does show some interesting characteristics that makes it pretty easy to understand how motors do what they do. Okay, so we have, in three-phase, we definitely have what they call a rotating magnetic field. Okay, and a rotating magnetic field is the key to the operation of the AC motor. Magnetic fields of the stator is made to rotate electrically around and around in a circle. Okay, stator being the outer shell, okay, and the rotor being the inner rotating part. All right, a second magnetic field is set up on the rotor, okay, and depending upon the type of rotor you have different kinds. You have squirrel cage and generally a wound rotor. Okay, the squirrel cage is by far the most common, and it's made to follow the magnetic field of the stator by being attracted and repelled by it. Okay, 3 sets of stator windings are placed. Okay, I'm going to basically read this and then we're going to see in the pictures what's happening. 3 sets of stator windings are placed 120 degrees apart. Why?
360 degrees in a circle, divided by 3 gives you 120.
Yep, you got it. All right, so the 3 phases, current passes through the stator windings. In other words, the current's being applied, the voltage is being applied to the stator windings. The current is a function of the resistance of the stator windings to start with, and then it's a function of the counter EMF that's produced, knocking down the applied voltage and developing a steady state or fairly steady state voltage internal to the motor, which is the implied voltage being countered by the counter EMF that's being developed by the rotating field. All right, and when we have a 3-phase current pass through the stator windings, a rotating magnetic field affects the travels around the inside of the motor core set up. In other words, you've got 3 individual sets of poles that are 120 degrees apart, or let's say you've got 6 halves of a magnetic pair that are 60 degrees apart, okay? So that they're continually, the ones that are opposite each other are working together, okay? So you've got 6 poles going around, and as they do, as one, as you saw, when it's at the top, it has 0 cutting action as far as the magnetic flux is concerned. As it starts coming down and it gets to the center of the spin, at the center it's got its maximum cutting action because you're cutting it at 90 degrees. Okay, up here you're cutting it at 0 degrees and it's gradually increasing. At that point it starts changing direction, going down, and at the bottom it's 0 again. Now it's changing from the 0 positive to 0 negative, and it's increasing in the negative direction up to a maximum negative, and back at the top it's going to 0 again, getting ready to change back to positive. And that's happening at 3 different parts of the circle. So each one is cutting at a different time. Each one's getting 0 a different time. They're each 120 degrees out of phase with another. They're getting their peaks at a different time. They're getting their valleys at a different time. And all of that stays consistently 120 degrees apart. The polarity of the rotating magnetic field is shown in the 6th position, marked off at 6-degree intervals on the sine waves representing the current flow in the 3 phases, A, B, and C. Okay, so we have a motor, we have a synchronous speed. Again, we'll talk a little bit about synchronous speed, so let me not jump the gun here. Okay, simply interchanging any of the 2-3 phase power leads reverses the change in direction. In other words, if I could take L1 and swap it with L2 and it would change directions. If I took and changed all 3 of them, it's right back to where we started. Okay? So you only change 2 of them. You could do L2 and L3, swap them. You could do L1 and L3 and swap them. So swapping any 2 of the leads would cause the rotation to go from clockwise to counterclockwise. All right, in this case, we're looking at a clockwise direction. The motor synchronous speed is the speed of the sensor's magnetic field, okay? So it's going at 60 hertz, okay? So what's a hertz? It's a cycle per second. So it's a circle per second, a rotation per second. So what does that work out to be? Again, we'll talk about that. The motor synchronous speed is the motor as the speed of the magnetic field rotation. So if we have 1 set of poles per phase, it would be called 2 poles. Okay. If I had 2 sets of poles per phase, it would be 4 poles. Okay, and again, we'll get into that. In order to develop torque, the rotor always turns slightly slower than the synchronous speed. Now, what are they talking about there? Think about it. If the rotor is a little bit slower than the actual synchronous speed, it's always trying to catch up. So as it's trying to catch up, it's developing torque in order to do that. All right? The motor actual speed is listed on the nameplate. Okay? Actual speed is always at rated load. All right?
Yay.
Here's where we're talking about synchronous speed. Okay, so it has to do with the number of cycles, which is F, frequency. Okay, the cycles per second. And 120 is taking into account the fact that I have 60 seconds in a minute, RPM, right? 60 seconds. And then I have 2 pi, okay, I'm sorry, I have
2 minutes.
2 poles associated with each winding.
So each pole takes a minute, you're saying?
Okay, so that's where you get the 120 times the frequency divided by the number of poles. All right, so the synchronous speed in this case, for example, if we had a 4-pole motor, which is what we were just talking about looking at, all right, at a frequency of 60 hertz. So I've got 4 poles times 20 times 10, okay, 1800 RPM. The fastest the motor can go at 60 hertz would be if I have 2 poles or 1 set of poles per phase, okay, and that would travel at 3600 RPM. Now, that's the synchronous speed. That's the speed that magnetic field is rotating within the stator, all right? It's not the speed of the rotor. The rotor is going to be slightly slower, And as it's picking up torque, it's going to pick up what they call slip. And as it slips, it's going to slow down just a little bit. And that is what they post on the motor as being its full load speed. Like for an 1800 RPM, it might be 1725, for example. It's not real lower, but it is lower than its total synchronous speed. All right, so we can get into problems and do that, but we have a problem there where you can look at how to calculate it. And again, remember it's poles per phase. So if I have a single phase motor, that would be 2 poles, okay? Now, an induction motor is pretty much like its name. There's no external voltage applied to it at all as far as the rotor is concerned. Okay, the induction is purely a function of what is happening on the rotor itself. There's induced voltages and currents in there, and that is what creates the magnetic field in the rotor that's trying to follow the rotation of the magnetic field in the stator. The AC current in the stator involves a voltage into the, induces a voltage in the rotating winding of the rotor and associated magnetic field. The stator and the rotor magnetic field then interact and cause the motor to turn. 3-phase motor, those motors start right up, vroom, because that rotation of the magnetic field happens immediately, or as close as you can get to immediately. And believe it or not, that's just how quick. Vroom. Okay. The motor and the stator magnetic field interact. Okay. Now, a 3-phase motor stator winding consists of separate groups of coils called phases. Okay, and designated as A, B, C. Now, C, A, B, C. All right, so what are these? All right, this would be a 4-pole because I've got
4 coils?
a north and a south. I've got for each set of poles per phase, a north and a south, right? So I have a north and a south, a north and a south. So I've got 4 poles per phase. So this would be an 1800 RPM motor, all right, connected in Y. We learned about that previous lectures. All right, the Y stator coil grouping, the phases are displaced from each other by 120 degrees electrically and contain the same number of coils connected for the same number of poles. In other words, you're not going to find one that's got 2 and 4 and then 2. Sorry, it doesn't work like that. They have to be balanced. Okay, so theoretically, this is a perfectly balanced motor. Theoretically, we never have the ideal. All right, so the poles refer to a coil or group of coils wound to produce a unit of magnetic polarity. Okay, and again, stator, rotor is what's going in between, right? The number of poles, let's count them. 1 set, A. So there's 4 poles per phase. B, 4 poles. C, 4 poles. ABC, 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 ABC. And again, that's how you get 3-phase power, and that's how you utilize 3-phase power. In other words, this could be a generator just the same as it could be a motor. Just whether you're putting electricity in or trying to take it out. Connected 4 poles, 3-phase induction. All right. And what they're saying is there is no electrical connection to the rotor. It's all induced currents and induced voltages in there. And that's what it's spinning. That's what's causing the spinning action. It's being pushed, and also, in other words, it's trying to repel and also attract. So as these change, because again, when they go from through zero back, they're changing polarity each time, north, south. Okay? So they're changing polarity every time they do that.
So it can't decide if it's attracting or repelling, so it just spins in circles.
That's correct. But since it's going like this,
Yeah,
as
technically,
it's
it's more like a
spinning in
wave.
circles. All right. All right, squirrel cage induction.
I still say it looks more like a gerbil cage.
An induction motor can either be a wound rotor or a squirrel cage rotor. The majority of induction motors are squirrel cage rotors. Rotor is constructed using a number of single bars short-circuited by an end ring. We'll see the picture of this in a second.
Ooh, they do say hamster wheel right there. That's what it looks more like, the hamster wheel.
Single bar short-circuited end rings and arranged in a hamster wheel or
I was getting ahead of you, sorry.
squirrel cage configuration.
It's the hamster wheel, or the gerbil wheel. See? There he's running in the little cage.
And you can see that they're shorted out on the end. Okay?
Little
That's
gerbil
what they're
wheel.
talking about there. And this
Running in
is,
his wheel. No, stop spinning. You broke it.
so let's go back.
Here we go. Yay. Kind of like going through
When
one of those
voltage is
tunnels.
applied to the stator winding, a rotating magnetic field is established. The rotating magnetic field causes a voltage and resulting current to be induced in the rotor. These rotor currents establish their own magnetic fields, which interact with the stator magnetic field to produce a torque, force that spins. All right, again, see you've got plates, generally speaking, a lot of times in there. There's your rotor going through. The ends are tied together. The resistance of a squirrel cage motor has an important effect on the operation of the motor. A high resistance rotor, low starting current. A low resistance rotor develops low slip and high frequency.
High efficiency.
High efficiency, sorry, yes. Okay?
Mm-hmm.
All right, squirrel cage speed torque characteristics. And again, depends upon what you want to pay for. Okay, you can see the type B ends up. There's your torque, synchronous speed, percentage of synchronous speed, I should say. Okay, and
So which of these three types would be the cheapest?
B.
Because it starts out the lowest?
It's just, yeah,
Would that mean that D would be the most expensive because it starts out higher?
it has high starting torque.
Ah.
Again, this is speed, okay? So it's got high starting torque, medium starting torque, low starting torque. Okay.
So that's
now-
what you're paying for,
Yeah,
that starting torque.
the torque. Considered a standard type, normal starting torque, low starting current, low slip at full load. Okay, and a little higher and this highest. So again, it's a function of what you're willing to pay for. You get into these, you've got a fairly high inrush at this point. Okay, when you're trying to develop that much torque at starting, you're talking a high inrush motor. This is a low inrush motor and medium in between. So this might be 6 times full load. This could be 15 times full load, just to give you an example. Okay. Squirrel cage operating characteristics. Motor normally operates at essentially a constant speed, close to that as synchronous speed. Large starting currents required by the motor can result in line voltage fluctuations. Once started, the motor will continue to run with a phase loss as a single phase motor. The current draw from the remaining 2 lines will almost double, and the motor will overheat.
That's not good.
Okay, but it will keep running. So that's why motors are provided with overload protection to shut them down when you lose a phase. So the motor will not start if it lost a phase. In other words, it won't be able to develop enough torque to get it running. Interchanging any 2 of the 3 power lines will reverse the motor direction. All right, so forward, reverse, not unusual there. Look at it. 1 to 3, 2 to 2, and 3 to 1. So from going the forward direction, you reversed 1 and the 3. Okay, this is one contactor, a forward contactor, and as it's coming over here, if you pick this up, it's reversed. The 1 will go over to the 3, and the 3 will go to the 1, which is what you're seeing there. And the 2 goes to 2. Again, like we were seeing before, they're electrically interlocked.
And kind of zoom in where they can see this moving.
Okay, you're unable to pick it up because they are electrically interlocked. Once you stop it, it'll pick up. And now the other one won't be able to pick up. And again, they're usually typically mechanically interlocked also, so that they can't physically close both simultaneously. All right, the rotor does not revolve at synchronous speed, but tends to slip behind. If the motor turned at the same speed at which the field rotates, there would have no relative motion between the rotor and the field and no voltage induced.
And we can find the percentage slip. Again, just like before when we were talking about those percentages, we're looking at that change over the original. So we're take the synchronous speed and subtract the actual speed to get that change on the top. You divide over what that original synchronous speed is, and then you're going to multiply by 100 to turn that decimal into a percentage. So a couple steps there. So let's look at an example.
That's what you get.
So in this problem, it says determine the percent slip of an induction motor having a synchronous speed of 1800 RPM and a rated actual speed of 1750 RPM. So we got to find that percentage change first, right? So we take our synchronous speed, which was 1800, and we're going to subtract our actual speed, which is 1750. What's the difference between 1800 minus 1750? It's only 50, right? So we're going to take that 50, divide it by our original synchronous speed, which is 1800, and again, we're going to get a decimal number. We want to multiply it by 100 to get that percentage, which in this case is going to be 2.78%.
Very good. Loading of an induction motor is similar to that of a transformer. Both involve changing flux linkages with respect to the primary and the secondary windings. Okay, and again, you're getting transfer between the two. Primary being where the supplied, and over here, secondary is the load, the drive end, right? The no load current is low and similar to the exciting current in a transformer. In other words, once you get a transformer magnetized, before that you have an inrush current, and once it magnetizes the entire core, then it stops at a steady state magnetizing current, and it'll stay there basically pretty much throughout the whole range of its use. When a motor is under load, the rotor current develops a flux that opposes and therefore weakens the stator flux. This allows more current to flow to the stator windings, just as an increase in current in the windings of a transformer results in a corresponding increase in the primary current. So it's kind of like a transformer motor, but not. Same operating principle though. Power factor. Okay, we've learned about that. I'm not going to go into it again. I'm not going to torture you with it again. But it's basically how much the percentage of inductive, or I should say, it's looking at the ratio of real power to total power. Okay, and again, it's expressed either as a percentage or as a decimal. We're not going to go into that. I'm not going to be testing you into that. I punished you last time around by doing that. I'm not going to do it again. All right, no load power factor is very low. In other words, actually, after you start picking up load,
It's going to be picking up more power factor.
right, down here,
Starting with next to nothing.
why? Because again, higher currents, you're drawing more current as you move forward, which is more induction in there. Okay. The moment a motor is started, it draws a high current called the locked rotor current. Again, mostly a function of the resistance of the windings. The induction motor starts at a rated voltage. Have locked rotor starts. Starting currents of up to 6 times their nameplate. High locked rotor current can create voltage dips or sags. Yeah. You ever notice when your air conditioner starts up outside, sometimes your lights dim? That's why. Okay? Because it's, and again, that just means maybe you need a little bigger conductor in there, so you're not dropping as much voltage as you think. All right, and the power lines, which may cause objectionable light flicker and problems with operating equipment. A motor that draws excessive current under locked rotor condition is more likely to cause nuisance tripping. Okay, in other words, you got that D style that's got that heavy inrush current. Okay, you've got to push your let's suppose you've got a breaker that's protecting your circuit, and if you set it up for an inrush current times 6 and it's actually drawing 15, so you push this up to say 12 times, well, it wasn't high enough, so you got to push it up higher to get it past there. So if you have tripping, and believe it or not, we had this during the last outage I had down there. We had a motor that they swore was bad, and I convinced them it was good because they were ready to change it out, and I said, just bump the setting up on the breaker, and guess what? They did. It ran just fine. Okay, and thanks. Learn these things. Now, it could be that you had a problem in there, but I was convinced by what we were saying that we didn't have a problem. So I stuck to my guns, and they finally agreed. All right, so again, dual speeds. Whenever you've got all right, dual speed, 1750, 875, which is just half, right? This is a series delta.
Because in that triangle,
This
like a
is
delta.
a parallel Y.
Because it looks like Y. Even though it's spelled W-Y-E.
Okay, one way you can control speeds, and again, you can do that with contactors set up to configure it that way as they open and close contacts. Okay, and this tells you how to hook it up. Something like that, you definitely need a hookup because that's not something that you're going to see in too many books. But there's a lot of them that have it. Single-speed AC induction motors are frequently supplied with multiple external leads for various configurations, okay, various voltage ratings in a fixed frequency application. In other words, what do I have? Two windings, so a 3600 RPM motor connected in Y. Okay, so if we look at 4, 5, 6, 4, 5, 6, 4, 5, 6, in low speed, okay, just like the transformer with the high voltage on the windings here, you're always going to want them in series. So 4 going to 7, 4 going to 7, 5 going to 8, 5 going to 8, 6 going to 9, 6 going to 9, T1, T2, T3, and then everything tied at the other end. So these would be internally connected right from the factory. All right, so that would be quite typical. Always